Welcome back, my dear friends. A very good morning, good afternoon and good evening to all of you, all the participants for TQM2 under NPTEL MOOC. And today is the 11th lecture, so which is the first lecture for the third week, and I am sure you have got your these assignments and you are quite comfortably placed considering the concept which are being covered. So, and as you know, I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember in the last class, which is 10th one, which was the last class for the second week, we discussed the unbalanced, balanced, and how the errors could be there. So, they depend on how. So I have given you the concept, but obviously there would be many ifs and buts depending on how the experiment was conducted, outliers being there, errors being dependent and all these things. But there are different ways to check whether the experiment is going as per the norm. So, some theoretical assumptions should be met. Obviously, in all the cases, all the theoretical assumptions being met in the practical sense may not be possible. So, with this I will continue the 11th lecture. So, if you remember, we were discussing on the residual plots, the QQ plots, the normality, and how we can find out some idea about the normality. So, this figure, which is 3.5 and 3.6 taken from Montgomery's book. So, here we have the run order or time being there on the for figure 3.5 along the x axis and along the y axis you have the residuals. Similarly, you have the predicted values and the residuals being plotted in the x axis and the y axis for figure 3.6. So, from based on that, so it is written that plot of the residual versus the run on time or run order or time is given in figure 3.5 and plot of residuals versus fitted values are given in 3.6. So, if the model is correct and the assumptions are satisfied, the residual should be structureless. In particular, they should be unrelated to any other variable including the predicted response. A simple check is to plot the residual versus the fitted values. This plot should not reveal any obvious patterns, and that should be true because if they are random, so obviously the randomness should be showing up in the calculations of the values which you are plotting. A defect that occasionally shows up on this plot is the non-constant variance. Sometimes the variance of the observation increases, the magnitude of the observation increases. So, that means in case you are taking for 160, 180, 200, 220, as you increase, the variance increases. This would be the case if the error or background noise in the experiment was a constant percent of the size of the observations. So this is the second point. So, it may become that if the size of the observations, if n increases, you are taking more and more observation, that would also have an effect on the variances. If the assumption of homogeneity of variance is violated, the F test is only slightly affected in the balanced equal samples of in all treatment fixed models, but obviously in the unequal size unbalanced model, the effect would be much more pronounced. The usual approach to dealing with non-constant variance when it occurs for the above reason is to apply a variance stabilizing transformation and then to run the analysis of variance on the transformed data. In this approach, one should note that the conclusion the analysis of variance applied to the transformed population only, not for the untransformed one. So, basically you change the population, do some transformation in order to give some semblance or normality or bring some of the assumptions in practical sense or in theoretical sense and do the experiment and do the calculations. So, obviously analysis of variance would be there for the transformed data, not for the untransformed data. So, few of the transformations, for example, if the observations follow the Poisson distribution, the square root transformation would be used. So, either you can find out y star ij, which is the new values which you will put in the cell. Cell means the matrix 4 by 5 or a by n, whatever it is, as square root of yij or yij star would basically be 1 plus yij square root would be used. If the data follows the log normal distribution, the logarithmic transformation would be used, where yi star would basically be the log value of the untransformed value. For binomial expressed as fraction, the arc sign transformation would be used, which means y star would be, I am not mentioning the word value ij, would be equal to the arc sign of the square root of y ij. When there is no obvious transformation, the experimenter usually empirically seeks a transformation that equalizes the variance regardless of the value of the mean, and then does the experiment accordingly. Now, the statistical test for equality of variance, which was very important. So, in the null hypothesis, it is sigma 1 squares is equal to sigma 2 square till the last value, which is sigma square suffix a, are all equal, and an alternative wing being that above is not true for at least one value of sigma square I suffix I, where I again I am mentioning varies from 1 to a. A widely used procedure is the Bartlett's test. The procedure involves computing a statistics whose sampling distribution is closely approximated by the chi-square with 1 degrees of freedom when the random samples are from independent normal transformation. The test statistics without going into the proofs would be given by the chi-square under the null hypothesis. It is 2.3026 divided by q by c, where the q and c values are given. So, it may be difficult for you to understand, but when you are solving the problem trying to understand, you can safely use these formulas as given in the book and do the corresponding calculations accordingly. So, this is the q value, this is the q value, this is the c value, this is the c value, and the pooled variance, sample variance of the ith population, which I will use another ink highlighter, is this. So, this s square suffix I is basically the square of the standard error for the ith treatment. I is equal to 1, 2, 3, 4 till a, and ni minus 1 is basically the sample size minus 1, because you are losing 1 degrees of freedom corresponding to the mean value being not known, and you will sum it up from, in the numerator you will sum it up from I is equal to 1 to n, and divide the whole thing by the total degrees of freedom for the corresponding pooled sample variance would be capital N, which is now n1 plus n2 plus n3 dot dot plus n suffix small n, I am talking about small n only, small n suffix a minus a. So, that would be the total degrees of freedom. So, from that you will get s square suffix p and do that calculations accordingly. We reject h naught only when the value, so it is on the left hand side. So, obviously, we will reject it or on the right hand side depending on how you are basically understanding. So, we will reject h naught if chi squares null hypothesis is greater than chi square alpha comma alpha a minus 1, which is the degrees of freedom. So, where chi square alpha comma alpha a minus 1, which is the suffix, is the upper alpha value point of the chi square distribution with a minus 1 degrees of freedom, the p value approach to the decision making could also be used. This test is highly sensitive to the normality assumptions, or else it does not hold. So, let us consider an example. If the plasma H example which you are considered, the normality assumption is not in question. So, we can apply the Bartlett test to the H rate data. We first compute the sample variance for each, which is the square root of the standard error. So, SI1 square is R, again I am not mentioning the values of the decimals, it is 400, S22 square is equal to 280, S3 square is 421. Oh, it should be basically not S22 square, it is S2 square, sorry, my mistake, which was 280, S3 square is 421, S4 square is 232. Then the so called pooled sample variances or standard error square would come out to be as given as 333.7. Now, from that we find out the value of Q as 0.21 and the value of C as 1.10. Place that in these values and you find out chi square on the null hypothesis as 0.43. So, from the table you can find out the chi square for degrees of freedom being, so A is what? A is 4, 4 minus 1 is 3, and alpha value is given as 0.05. From that you find out 7.81. So, we cannot reject the null hypothesis. So, there is no evidence to counter the claim that all the 5 variances are the same. So, this is the same conclusion reached by analyzing the plot of the residuals versus fitted values. So, you are basically have seen the diagrams, now you are basically trying to corroborate that with your test. Other transformations are for variance stability transformations. So, you will basically if the relationship between the variance or standard deviation and mean value, if if the standard deviations is basically proportional to constant and the alpha value is 0, and then there is no transformation is utilized. If the standard deviation is proportional to the square root of mean value, then you use the square root transformation. When it is proportional to the mean value, then you use the log transformation. When it is proportional to 3 by 2 power, you use the reciprocal transformation. And when it is proportional, when it means I am using the word it for the standard deviation. Standard deviation is proportional to the square of the mean value, then you use the reciprocal transformation. So, these are just for information, but if you get the idea for problems, solving the problems, you will get everything kick starting. Now, you want to interpret the results. The factors involved in an experiment can be either quantitative or qualitative. A quantitative factor is one whose levels can be associated with points on a numerical scale, such as temperature, pressure, time, humidity, so on and so forth. Qualitative factors, on the other hand, are levels which cannot be arranged in order and magnitude. So, it can be operators, batches of the raw materials, shifts are typical qualitative factors, because there is no reason to rank them in a particular way as we wish. So, it can be the operators who are coming, operator 1, operator 2, operator 3, or it can be say for example batches of raw materials which are coming from vendor 1, vendor 2, vendor 3, and so on and so forth. The experimenter is frequently interested in developing an interpolation equation for the responsive variables in the experiment. This equation is an empirical model of the process that has been studied, and we basically do the studies accordingly. We initially try fitting a linear model to the data. Say for example, we say that y is equal to a type of multiple linear regression beta naught plus beta 1 into x1 if there are only more than one variables plus epsilon. If there is only if it is a simple linear regression, you will basically have y is equal to beta naught plus beta 1 into x plus epsilon. If it is a multiple linear regression, it will be y is equal to beta naught plus beta 1 into x1 plus beta 2 into x2 dot dot till beta k is equal to xk, considering there are k such x values, different x values which determine the values of y. So, where beta naught, beta 1 are the known parameters to be estimated, and epsilon is basically the random error term. So, if you basically fit the data corresponding to the power and corresponding to the linear model and corresponding to the power being the quadratic model. So, you are trying to fit the h rate along the y axis, the power along the x axis, but in the first case you consider the power's relationship with the edge as linear, and in the second case you consider the power relationship with the h rate as quadratic. So, what you are trying to fit, you are trying to fit the mean value. So, if you see the diagram here, so in this case the linear plot is there, the mean values are somewhere here. This I am just giving a very rough estimate, and if I go for the quadratic model, so the mean values are almost falling here. So, this is just a guesstimate or estimate which I have done and tried to show you in front of you. There can be other model fitting also. So, it need not be quadratic is the best, it can be cubic, it can be square root, whatever it is. The quadratic model is made since the linear model does not produce a good fit. The model is given. So, this y value which I have taken, that if you remember that we had considered, let me put the equation in a right perspective. Y is equal to beta naught plus beta 1 x1 plus dot dot plus beta k xk plus epsilon. So, these x's which I have, I will use some different color. These x's which I are using, this I am considering they are not linear, they are quadratic. So, this is where it is coming. So, something here, it can be square. So, in this example the quadratic model is the best fit. So, you find out the values of beta naught as 1147. Again I am not mentioning the decimals. The value of beta 1 corresponding to x only comes out to be 8 point something, and so called beta 2 corresponding to x square, which I consider as x suffix 2 as the second variable. So, then the empirical model is used to predict H rate at power settings within the regression of the experiment and the model. In other cases, the empirical model could be used for the process optimization and the work can be done accordingly. Some graphical comparison of the means. It is very easy to develop a graphical procedure for the comparison of means following an analysis of variance. Suppose that the factor of interest has A levels. So, this A value is, if you remember, those were the number of treatments, and that y1 bar, y2 bar. So, this 2, 1, 2, 3, 4 what I am saying on the suffixes till ya bar are the treatment averages. If you remember, that is what we have calculated. So, y1 bar is basically summation of y11, y12 dot dot y1n, the first one corresponding to the treatment, the second number corresponding to the sample observation. If it is basically the eighth treatment, it will be, again I am repeating, please excuse me, it will be ya1 plus ya2 plus dot dot yan divided by n. So, that values are given. If we know sigma, any treatment average would have a standard deviation given by sigma by square root of n. This is basically the actual concept of central limit theorem, which I did discuss among the first 7 classes, if you remember. Consequently, if all factor levels means are identical, the observed sample means y bar suffix I would behave as they were a set of observations drawn at random from a normal distribution with a mean of y bar dot dot, which is the sum of all that is the average of the average, the grand average, and with a standard deviation of sigma by square root of n. We visualize a normal distribution capable of being slid along the x axis between y1 bar, y2 bar till y bar by a bar are plotted. If the treatment means are all equal, there should be some position for this distribution that makes it obvious that y bar I values were drawn from the same distribution. If this is not the case, y bar I values that appear not to have been drawn from the distribution are associated with factor levels that produce different mean responses depending on the outcome of the experiment which is going on. The only flaw in this logic is that sigma is known. So, if you basically follow the books, the paper of Box, Hunter and Hunter, they point out that if you replace sigma with the mean square error from the analysis of variance and use a t distribution with the scaling factor of mean square divided by n. So, that is the whole square root, because you have sigma square by n, square root of that. So, MSE suffix E is the mean square, you find out the square root, n you find out the square root. So, everything is given in the square root as given in this formula. So, instead of the normal case, in such an arrangement for the H rate data, for example 3.1 is given, focus on the t distribution shows as a solid line curve in the middle of the display. To sketch the t distribution, simply multiply the abscissa t value by the corresponding, so the value of which I just mentioned is square root of MSE divided by n, which comes out to 8.13, and plot this against the ordinate t at that time. Because the t distribution looks more like a normal distribution. Again, this is the point which I mentioned time and again, as the sample size increases, the t distribution becomes exactly equal to the normal distribution. And another point which I did mention, when you are writing the t distribution along the x axis, either for the interval estimation or of the hypothesis testing, technically it should be t suffix 1 minus alpha, but in the case as it is symmetric, we use minus of t suffix alpha. This is true for the z distribution also, because it is symmetric, definitely is symmetric, but may not be true for the case of chi square and f distribution. That is why you use on the left hand side chi square suffix whatever the degrees of freedom is 1 minus alpha, and if it is on the right hand side, it is chi square whatever the degrees of freedom comma it is alpha. Similarly, for f would be m comma n if m and n are the degrees of freedom, or m minus 1 n minus 1 whatever the degrees of freedom are, comma if it is on the left hand side the value is 1 minus alpha, if it is on the right hand side it will be f with the corresponding degrees of freedom comma alpha. And obviously, if it is both sided for the chi square and the f distribution, those 1 minus alpha and alpha get replaced by 1 minus alpha by 2 and by alpha by 2. So, this sketch is usually easily constructed by the eye. So, if you want to be more precise, there is a table of the abscissor t values and the corresponding ordinates. So, the distribution can have an arbitrary origin, although it is usually best to choose one in the region of y bar I and do the calculations accordingly. So, here you have basically trying to plot it. Visualize sliding the t distribution as shown in figure 3.11 which is there in front of you in the slide along the horizontal axis as indicated by the dashed line. So, you move on to the left and the right and examining 4 means plotted in the figure. Notice that there is no location for the distribution because either it can increase or decrease, that means it can get more flat or can be more spiked depending on the change of the variability. Notice there is no location for the distribution such that all 4 averages could be thought of as typical randomly selected observations from the distribution. This implies that all 4 means are not equal obviously, but it would also mean that if you can do a visual test very simply and being careful whether the variability is increasing or decreasing or is constant. Thus, the figure is a graphical display of the ANOVA results. Furthermore, the figure indicates that all 4 levels of power of 160, 180, 200, 220 produce mean H rates that differ from each other, and obviously it will give you an idea that the mean values, which is basically mu 1, mu 2, mu 3 are not equal. So, at least one of them being not equal obviously would negate your null hypothesis. So, from here you can find out the etching and you can do your example accordingly. So, now consider the contrast and another type of problem. Many multiple comparison methods use the data of contrast. So, we are basically trying to contrast them and compare them and do the analysis. Consider the plasma etching problem again. Because the null hypothesis were rejected, we know that some power settings produce different H rates than others, and it has been proved in the examples, but which one actually causes the difference is basically the main question we need to answer. We might suspect at the outset of the experiment that 202 or 220 produce the same H rate, implying that the null hypothesis can be framed as mu suffix 3 is equal to mu suffix 4, which is the third and the fourth, which is the 200 and 220 with respect to the alternate hypothesis, which is they are not equal, or equivalently the difference between the mu values for the third and the fourth is 0 with respect to the alternate hypothesis that they are not equal to 0. If we had suspected at the start of the experiment that the average of the lowest value of the power did not differ from the average of the highest power, then the hypothesis could have been framed that 1 plus 2, which is the first and the second, is equal to the third and the fourth, or and the null hypothesis, an alternative hypothesis could be 1 and average of the first and the second is not equal to the third and the fourth, or else it can be implied in the different way where you find out the differences between the first and second minus the difference sum of the third and fourth. That means you add up the average of the first and second, which is 180 and 160, add that value and from that minus the value average value of 200 and 220. If it is 0, that is under the null hypothesis. If it is not 0, that is under the alternative hypothesis. So, in generally a contrast is a linear combination of the parameters of the form, given that I want to check that I basically have a function. So, I want to find out a convex combination of these values of mu 1 and mu 1, mu 2, mu 3, mu 4 or till mu a. So, in this case if it is from 1 to a, so it will be multiplied by mu's will be multiplied by the corresponding c's. So, this is C1 plus mu 1 plus C2 into mu 2 dot till C a into mu a, where the contrast constants are given as C1 to Ca and they sum up to 1. So, what you are trying to do, you are going to basically load them and less load them depending on what is the values of C. That is, the values of C's are 0. Both of the above hypotheses can be expressed as null hypothesis. The contrast sums are 0 against the alternative hypothesis, they are not 0. The contrast constants of the hypothesis in equation 1, which in 3.23 for the equation done, is C1 is equal to C2 is equal to 0 and C3 is equal to plus 1 and C4 is equal to minus 1. Whereas the hypothesis for equation 3.24, they would come out to be C1 plus C2 is equal to 1 with respect to C3 and C4 is minus 1, because the sum obviously adds up to 1 in both the cases, is to 0 in both the cases. So, equations are the formulated are basically the corresponding hypothesis in the previous slide that has been done. Now, testing the hypothesis involving contrast can be done in two basic ways. The first method uses a t-test. The following statistics is calculated to test the hypothesis mentioned in the previous slide. So, in T naught, which is the null hypothesis T values, is equal to summation of Ci into y bar I, because mu's has to be replaced by the corresponding best estimate, which is mu hat, which is equal to y bar, and the test statistics obviously would have divided by its so called standard deviation divided by the degrees of freedom. So, that is what is done. So, mean squared error divided by n into the sum of the Ci's would basically be the denominator which you have. The null hypothesis would be rejected if T naught exceeds T. So, now you are taking both the tests. So, obviously, it should be on the left hand side or on the right hand side. So, the degrees of freedom are n minus a values. So, this a values would basically be corresponding to the number of such etchings which you have. Capital N is basically n1, n2, n3, whatever it is, you sum them up, and this alpha by 2 value is basically coming to the fact that this is a both sided test, not a one sided test, either left one, right one, remember that. The second approach uses is basically F test. So, now the square of a t random variable with the degrees of freedom being calculated with one numerator and v number of denominators would give you the degrees of freedom. So, therefore, we will have the F would be, if you remember, the F distributions can be found out as we have mentioned, the chi-square, the T distribution and the F distribution in one of those 7 classes, first lectures in the fag end. So, you can find out the F value on the null hypothesis, as in the numerator you have the square of the value of C's multiplied by the corresponding estimate of mu hats, which is y bar I. So, it will be C1 into y bar 1 plus C2 into y bar 2, so on and so forth, plus dot dot till Ca suffix a, obviously these suffixes, into y bar a, divided by so called, if you think a simile on these lines, it is the mean squared error divided by n multiplied by the square of Ci's, which if you remember, the sum of Ci should be 0. So, the null hypothesis would be rejected if the value of f naught under naught is greater than f. Now, see the values which you have in the suffixes of f, it is alpha. And one is basically the degrees of freedom, the other degrees of freedom is n minus a. Now, why alpha? Because you are considering either left or the right hand side, not the two tailed. We will start the orthogonal contrast. So, the two contrast with coefficients Ci's and Di's are orthogonal if you multiply them, obviously the values is 0, or for an unbalanced diagram. So, considering that n1s, n2s, n3s are all different, it will be multiplication of n and then sum it up is equal to 0. So, that means summation of ni, ci, di is equal to 0. So, that is the orthogonal contrast. For a treatment, the set of a minus 1 orthogonal contrast partitions the sum of the squares due to the treatment into a minus 1 independent single degree of freedom components. Thus, tests performed on orthogonal contrast are independent and you can pass on much better judgment for that. There are many ways to choose the orthogonal contrast coefficient for a set of treatments. Usually, sometimes in the nature of the experiment should suggest which comparison would be of more value, whether it is the orthogonal one or when you are going to basically do the contrast accordingly. So, with this I will end this 11th lecture, and thank you for all of you for your attention, and we will start on the 12th one and correspondingly discuss more about ANOVA and the design of experience. Have a nice day. Thank you.